Alright, this is the Physics 2212 Lab 4 on circuits, and my name is Jonathan Paparo. The purpose of this lab is to use the principles of energy conservation, loop rule, and current conservation, charge conservation, and definition of steady state. In this lab, you will predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. The physics principles that are used are the conservation of energy and charge and Kirchhoff's circuit laws. The loop rule states that the sum of charges and potential the sum of the changes in potential around closed circuit path sum to zero. And then the node rule is that the sum of currents flowing into node is equal to the sum of currents flowing out of the node. And then we also use Ohm's law, the resistors and capacitors in series and parallel, capacitance, time dependence, and the natural log equivalent of that. And then for an introduction for this, the actual values of current and voltage given by the model match those predicted by the formulas. In an RC circuit, the magnitude of current is time-dependent based upon exponential equations, as you'll see later. That's the assumptions and models. Using an online ideal model of a circuit in order to observe the behaviors and resistors and capacitors in various combinations. The assumption is that the resistance in the wires is negligible and the resistance in the ammeter is negligible as well. The energy conservation equation for this circuit is the V capacitor and the V resistor equal to 0, and that is true because of the node rule, is what I'm trying to say. Experiments and observations. The system is the circuit and the surroundings are everything else. And part 1, the actual reading was 0.020 amps. Then replaced 1 ammeter with a voltmeter, and the readings were delta V is equal to 3 volts and I is equal to 0, which makes sense. And then measuring the potential across the different segments, this makes sense as it's negative with the resistors and positive, and then those two cancel out, and the sum of the potential is 0, which makes sense once again with node rule. Okay, so as you can see here, the batteries raise the potential, the resistors lower the potential, and the wires and the ammeter do not cause any potential change, as was also shown in the last slide. So now we connect an ammeter in parallel with the 100 ohm resistor, and this caused the ammeter to raise to 0.06 amps because less current is now going through the 100 ohm resistor. And as you can see, there's the raise. And Ohm's law was used to find these values. Okay, the experiment and observations. Now the battery was connected to a 10 ohm bulb and capacitor in series, and then the bulb initially shined and then faded to nothing, and the current decreased from a max to 0. And then we disconnected the battery after charging the capacitor, and then the bulb does the same thing again. And then the 10 ohm bulb had a 15.45 second charge and a 15.2 second discharge, and a 27.6 second charge and a 27.52 second discharge. As you can see, those are nearly identical to each other in terms of second charge and second discharge. And then here, the delta V and time data was used to find the slope of this graph right here with the natural log of delta V over VO versus time. And the slope of that will give us that the RC took 7.07 seconds, but our expected was 6 seconds. So yeah, and this data was for a 9-volt battery and a 200 capacitor and a 30 ohm light bulb. And then our sources of error, there shouldn't be much because it's a computer model. For the first what if question, because I'm running low on time, I'll just give the answer. An emitter in real life has a small amount of resistance, so the circuit current readings would be slightly lower. And the assumption made is the resistance of the wires in emitters is negligible. And then for the next what if question, the simulation showed the capacitor charging immediately, but in real life, objects have resistance values that would slow down the charging process. So in the model, it was instantaneous charging, but in real life, it is not. It takes time. All right, thank you. This is my Physics 2212 lab. Have a good day.